In this video, we will perform a 3D thermal modeling of a cylindrical lithium-ion battery, which is this one. So first, we are going to download the files. And in this case, as you can see here, we only have 2 files, and we will download the PDF one, and we'll go through the instructions step by step. And we'll open it. By the end of this video, we'll be able to produce results that are similar to the one which we have here. So we will have a 3D cylindrical cell, and there's an airflow that's used to cool the cell. And also we will have a graph which shows the minimum and maximum temperature through the duration of the simulation. Now we'll start the instructions. So the first step is to open a file that's called lithium-ion battery 1D for thermal models file. Okay, the purpose of this file is to have the electrochemical part of the simulation ready for you guys, so you can just build in the thermal model on that one. Okay, so the first step, I'm going to open this file. So we'll go to the files, application libraries, and we are going to open it from here. Thermal management, and this is the file which we need. Now we have the file ready, and as you can see here, we have the parameters, and we have some functions and variables and so on. And also the lithium-ion battery model is already set up for us. So we can start right away with the heat transfer model. In this case, where we will need to add a 3D component here. Okay, and then we'll add the physics for the thermal and airflow, in this case, to be able to do it correctly. But I will not follow the instructions here. I will go through the basic, and I will start from the scratch. We will build this model, which is the electrochemical model, because although it is very similar to the first video, there is a slight changes that you need to know how to do them, because they are important for you guys. Okay, so although I will go a little bit quick with this part, but I highly recommend you to watch it and grasp what's going on with it. From this file, we are going to save the parameters to be able to build this model from scratch. So I will save it in the desktop and save. So I will open the PDF file for only this electrochemical part, which is different than the first video. And to do that, I'm going to open the PDF file for this electrochemical part. The PDF file is not available on the console gallery website. So in this case, we are going to open it from here. So we'll go to the application libraries, and we already have this model, and we'll open the PDF document for this one. Okay, now we have, this is the PDF document for the electrochemical part only, and we will go through this file. So we'll start with the model instructions from here. So we'll go to the file and a new one. So we'll go and select 1D. This is only electrochemical, and we are going to go to the lithium-ion battery. We'll add this one, and we'll click done. We are not going to add any study at this time. And the first step we are going to do is to load the parameters, and then we will build the geometry, which is very similar to the first video. And now we'll go to the definitions, and here is something new for you guys, which is to use the explicit here in the definitions. And the purpose of using explicit is to simply assign a domain or a boundary to a specific name. So for example, let's say I'm going to assign the first domain, which is this one, to the negative electrode. Okay, so later on, when I am in the lithium-ion battery model here, okay, I can simply choose if I want the negative electrode or any other domain. So as you can see here, I have selected negative electrode. Only this domain had been selected. This will make it easier for us to select the boundaries and domains right away from the list, instead of every time going to the graphics window and select them from here. Okay, so now we are continuing the definitions, and we will add another one for the separator and for the positive electrode. We also can add 2 more for the boundaries, for the negative and positive boundaries, or the current collectors. And in this case, we'll choose boundary. After that, we'll add the materials. And for the materials, I highly recommend you guys to first add the electrolyte material. Okay, so once you add it, you can see here the electrolyte material is assigned for all domains. Okay, and that's fine. Keep it as it is. And then we'll add the positive and negative electrode, the graphite and alamo. And we will close the material. Now we can go to the lithium-ion battery here, and we are going to do something very similar to the first video. So we are going to add porous electrode and type in the required information. This is the negative electrode, and we need to make sure it is assigned only to the negative electrode. And to just make it easier for us, we can also rename this one and have it as negative electrode. Okay. And now we will need to specify the electrode material. We have it as graphite, and we will type in the information. Now we'll move to the particle intercalation, and we also need to specify the material. So make sure you include the heat of mixing. And moving to the porous electrode reaction, we will also need to select the material. Okay, now we are done with this step. We are going to add an attribute, and in this case we'll choose the porous matrix double layer capacitance. This is important, especially if we are considering the resistance and considering the thermal simulation. And now we can move to the positive electrode. So we'll add another porous electrode, and we can rename it to be positive electrode. And we are going to choose the positive electrode domain only. Okay, as you can see here, there is still a problem. So that means we haven't selected any domain. So this means in the definitions here for the positive electrode, no domain was selected. So I need to come here, and to fix this issue, I need to select it like that. Okay, so now going back to the lithium-ion battery, porous electrode or the positive electrode. Okay, even with this selection, there seems to be a problem, not applicable. So that means there's a problem. Most probably it is from here, because at the beginning here we changed this one to be only applicable to the negative electrode. It should be to all domains, because we are considering the negative separator and positive electrode as well. So in this case, to avoid any kind of problem. So going back to the positive electrode, and we are going to select the required material for the electrode properties. It's going to be LMO. Now moving to the particle intercalation. And we will also include the heat of mixing. And for the porous electrode reaction, we will need to change the material to be LMO. And we'll close the positive electrode with the double layer capacitance. Now we will add a domain that's called separator. That's something we didn't use in the first video. The separator is simply assigned for the electrolyte. although we have here electrolyte, okay, but if we have some additional information, we will usually add a separator domain in this case, and we will assign that only to the separator, and we have the electrolyte volume fraction here. So that's the reason why we are adding this domain. Regarding the boundaries, we will add the electric ground, and we will select the negative current collector, and then we will add the electrode current density, and that will be for the positive current collector. And here we need to specify the current, which is IAP. As you can see here, the color has turned to be yellow, so that means this variable is unknown, and we are going to define that soon. But before going to the variables, we will need to finish and complete the lithium-ion battery section here. Then we are going to define the variable later. So now we will add an initial values, and this one will be only assigned to the positive electrode. And we are going to use this information here. It's going to be negative this value. And now we'll move to the initial value 1. Now we are almost done with this model, which is the electrochemical part. But keep in mind, we need to add something called shared properties. Okay, the purpose of this shared property is to have a property, for example, a temperature, to be shared between the electrochemical part and the thermal one. So we will add a model input here. And in this case, it has been already set to be temperature, but in case you have another variable which is or another input that's not a temperature, you can just simply change it. And here you can just search for temperature and you can filter it. Now we will define the current. First we'll add a function that has the waveform behavior. And in this case, just for you to get an idea how it's going to look like. For now we have the sine wave, but we're going to change it to be square, like that. And the angular frequency will be modified to be like this. Okay, so now we have changed it to be in this way, and we have the time here to be related to our simulation needs. Now we can add a variable for the applied current. We will need to add props to collect the information of the cell voltage and the current. And we are going to add a domain point prop. And the point that we're interested in is the positive current collector here at the far right side. And now we are going to expand this one and select the point prop expression. And for this one, we'll change it to be from the electrolyte potential, we'll change it to be electric potential. And the variable name will be changed to be this one, cell voltage prop. And now we are going to add a plot. And the last step here in this file is to add another global variable prop. Okay, so since this is a global variable, so we didn't need to assign it to any domain or boundary. So we only have I app over I1C, like that. And we're going to change the name of this prop, or the variable name. Now we have the electrochemical part ready, and we will start the 3D modeling for the thermal part. The first step here is to open the electrochemical part, which we have already completed, and we are going to continue from here onward. So we are going to add a 3D component in this case for the battery. So now we have component number 2, and this one is a 3D component. Now we'll add physics. And we are interested in the fluid flow, single phase flow, and we'll select laminar flow. And we'll add this one to component number 2. Now we'll add the heat transfer physics, and make sure you select the correct one, which is heat transfer in solids and fluids. After having these two physics, now we need to add a multi-physics coupling, and in this case we are going to select non-isothermal flow. And in this case we are coupling the two physics, which is the fluid flow and the heat transfer one. We need to add some parameters to be able to create the required geometry and also to have the velocity of the airflow. And these parameters will be added in the parameters list. After entering these parameters, now we can create the geometry, and we'll go to the geometry and we will add a cylinder. We'll specify the radius and the height of the battery. And we'll build the selected and choose transparency. Add another cylinder for the mandrel. Now we'll add the third cylinder, which is for the connector. We can combine all of these cylinders using union. And we'll come here and we'll click Ctrl A to select all of them. After constructing the battery cell, we need to construct the container for the airflow, which is here, this one. What we have done so far, we have just built this battery cell, and we need also to build the container for the airflow, for the inlet and outlet, and also we need to as well account for another cell, which is in this location here. We will add a block and type in the required information. Now we will add intersection, and we are going to select all, Ctrl A. Two blocks are needed for the airflow. Here in the difference, we need to select the objects that we need to add or to keep. And in this case, we're going to select these three objects. And now we'll select the one which we want to subtract. And we'll click Build Selected. Now we have the geometry almost ready for us. We only need to add mesh control faces, which is helpful when we are doing the meshing later on. We need to select boundaries number 6, 15, and 26 only. And there are two ways to do that. The first one is to just simply write the number of the boundaries. And the second way is to use the selection list, which is from home, and will show the required window. And here we can select boundaries 6, 15, and 26. Right click and select Add to Selection. Now the geometry is ready and we can move on to the definitions. We're going to use explicit in the same way that we used it in component number 1 when we were building the electrochemical component. This one will be for the flow compartment, and we'll select domain number 1. We will add another one for the active battery material, and that will be for domain 2. Add one more for the battery connector and select the associated domain. And now we will add 3 more explicits. For the inlet and outlet, make sure you are choosing the boundary here. And it will be for boundary number 1 for the inlet. And for the outlet, we can select it from here, which is this one. An additional one will be added specifically for the symmetry planes. And for this one, we will select boundaries number 2, 5, and 22. And for the can, the boundaries are going to be these boundaries. Now we will define an non-local coupling, which will be used to collect the average temperature of the battery in the active material. This will be used to feed the electrochemical part. Okay, let me just illustrate it from here. For the thermal model, now we will introduce a non-local coupling, where we are going to collect the average temperature of the active material. This average temperature will be fed to the cell model or the electrochemical part, and then the simulation of this electrochemical part will generate a heat. This heat will be given to the thermal model as an input, and so on. So it's like a cycle. Each one of these models is giving one thing. So the thermal model will give away the average temperature, and the electrochemical model will give the heat generation. Now we will add the average non-local coupling. And this will be for the active battery material. To connect the average temperature of the thermal model to the electrochemical part, we are going to use a shared property. And for the temperature, it will be this value, which we are getting from component 2. And now we will add a non-local coupling for component number 1, an average, and this one will be for all domains. The goal here is to calculate the mean heat source, and it will be delivered to the 3D model. And now to make sure the heat source or generation is delivered correctly to the 3D model, we are going to go back to the component number 2. And in this case, we are going to define a variable. And here is the information for the average heat source variable, which we are getting from the 1D battery model. Now we will add probes to collect the minimum, average, and maximum temperature in the same manner as what we have done in the last video. And this will be for the active material only. And we'll repeat the process for the others as well. After completing the work of the props, now we are done with the definitions and we can move to the materials. We will add it to the component. As you can see here, we have two materials that are exactly the same. This one and this one, right? And soon you will know why we are adding the same material twice. Now let's assign each material to a part. This steel will be for the battery connector. And the air for the flow compartment. And for this steel, we are going to change the geometric entity level to be boundary, and it will be only for the can. So this will not affect the battery active material. Since this is a cylindrical cell, we are going to add a cylindrical coordinate to be able to use the orthotropic thermal conductivity in the active material. And to do that, we'll go to the definitions and coordinate systems, and we'll choose cylindrical system. Now we can move to the heat transfer in solids and fluids. We'll go to physics, domains, and add a solid. And this will be for the battery active material. And from the coordinate system, we're going to select cylindrical system. In this case, we can change the thermal conductivity to be user defined, and this one will be diagonal. And we'll modify also the density and CP. After this, we can add a heat source, and it will be also for the active material. The heat source will be QH, which is the variable that we defined earlier. And for the laminar flow here, just make sure the domain selection will be only limited to the flow compartment. And for the fluid here, also change the domain to be flow compartment. We are limiting it to the air. Now we can add a boundary condition, which is the temperature. And from here we'll select inlet. We need to specify the temperature of the inlet. For the outflow, we can add a boundary, and we will select outflow. And from the boundary selection, it will be the outlet. To continue modeling the airflow, we will go to the laminar flow here, and we are going to use the physics for the laminar flow, and we will choose the boundaries and select outlet. And this one will be outlet, and for the pressure conditions, we will check the normal flow box. For the inlet, we will add a boundary that's called inlet, and we will choose the inlet. And the velocity of the air will be Vn. Now we can add a boundary that's called symmetry, and in this case we'll choose symmetry planes. Now we're remaining with the last few steps in the heat transfer model, and we'll change the reference temperature to be the initial temperature. We will also perform the same modifications on the initial value 1. Now we can move to the mesh. And here I will follow the instructions in this file. I will start with the size. And we'll specify this one to be for the domain, and it will be for the flow compartment. And from here we'll choose fluid dynamics. Now we can add a study. The first one will be stationary. And here we need to make some modifications because this study is specifically for the airflow. So we are going to uncheck the lithium-ion battery and the heat transfer in solids and fluids. Then we can add a current distribution initialization. And this one will be applicable only to the lithium-ion battery. So we are going to disable the others. And also don't forget to disable this one. And we need to do the same thing in the stationary study. We also need to disable this. Now we can add a time-dependent study. And for the output times, we are going to use these times. In this way, we are specifying the times which we are interested at. So there is no need for the solver to spend a lot of time in very small steps. In this study, we are not interested in the laminar flow. Now we are going to make some changes to improve the solver. And here is an explanation for the reason of performing these changes. Since the computation is now completed, so we can start the post-processing and plot the required plots. So for the first plot, we are going to make some adjustment or modifications for prop plot group 1. And for this one, we are going to edit the title and make it manual. And we will type cell, potential, and load. And this plot will have two axes. The label of the y-axis will be cell potential. And the secondary y-axis label will be battery load. Then we will change the position of the legend. Now we will edit the legends here. To have the battery load curve, we can simply duplicate this one and choose I_app over I1C and modify the legends. For this curve, we just need to make sure it is plotted on the secondary y-axis. Now we will change the labels of these graphs, and this one will be the battery load, and the other one will be cell potential. We can also rename this one to be load cycle to just make it easier for us to distinguish what this plot is about. Now we can move to the second plot. And we can modify the title of this plot and the legends. And for this graph, we're only going to keep the minimum, average, and maximum temperature. So we don't need to show the applied current in this one here. So we're only going to keep these three. And to show the battery load in this graph, we are going to add a table graph here. And in this case, we are going to specify which column that we need from the table. And to do that, we are going to choose it manually. We are interested in this one here to show the load. Just make sure you specify this one to be for the secondary y-axis. And we can change the label to be battery load. And the other graph, it's going to be the temperature. And just to make sure the plot is plotted correctly, we will come here and click plot. Okay, so we have it ready in this case. Now we are done with this graph, and to produce the last graph, we need to follow several steps. Okay, the first one, just make sure you are clicking in the component 2, and then we will go to the definitions, and we'll add adjacent. Then click add, and select active battery material, battery connector, and mandrel. Just make sure you select the interior boundaries checkbox. Now we can rename this one to be battery surface. After that, we'll go to the results toolbar and select more data sets. From here, we'll choose solution. And from the component, we'll choose component 2. Now we will add a selection by going into the attributes and choose selection. From the geometric entity level, we will choose boundary. And from the list, we will select battery surface. And then we will click in the transparency button. Now we can add a 3D plot. And we'll change the label to be temperature and flow. And from here, we will clear this checkbox. And we will not specify the dataset. If I click plot, you will see nothing here. So we're going to add a surface to be able to see the surface of the battery. And to do that, we will add a surface from here. And from the dataset, we're going to select study 1 solution 1. Then we will choose the time to be 1500. For the expression, we are interested in the temperature. And for the coloring, we are going to choose thermal light. Now we'll be back here and click plot. And as you can see here, we can see the battery and the temperature distribution in this case. Now we are only remaining with the flow. We just need to show it. And to do that, we are going to add a streamline. From the data set, just make sure you are choosing this one. And we will also have the same time, which is 1500. Regarding the expression, we are going to choose the velocity. And to do that, we are going to click this icon here, replace expression, and we will go to the laminar flow, velocity and pressure, and choose this one. Double click. And from the positioning here, we will choose unselected boundaries. Now we will select the inlet, and from the line style, we will choose ribbon. Now let's try and click plot. Now we can see the stream line of the airflow. However, as you can see, the color of these lines is only red. So we need to do some modifications to have the proper coloring. And in this case, we're going to right click and choose color expression. And we already have the correct expression, but just in case you have a different one, you can just choose it from here. You can just follow the instructions here to get the right one. which is just simply, it is in this place. This one, it's this one. And then click plot and zoom extend, and we're only remaining with the final touches. We will change the label of this graph to be temperature versus time. And that's it. We are done with this tutorial.